So I don't remember I don't remember exactly where we left off, but I know we're dealing with our semiconductors, semiconductors. So I want to talk through some of those aspects again as kind of a little bit of a review. We'll skip into the kind of directly relevant content, and then we'll move into some practice. Okay? So metals conduct electricities and non-metals do not. So what we talked about last week is that when we looked at metals in a bulk material, you have a valence band, and that's where all of our valence electrons kind of occupy. We also have a conduction band shown above. That conduction band is white, meaning there's no electrons in it. Okay? And so when we're looking at our metals, when we put an electric current to it, our electric current can cause our electrons to excite from our valence band into that conduction band really quickly and easily, and so our electrons can effectively oscillate back and forth and move from one side of our material to the other side. When we go through and look at nonmetals and we pump electrons into that, there's a gap between the valence and the conduction band. That's what's known as our band gap. Okay? For our nonmetals, that's a really large gap, which means to get enough energy to cause your electron to excite from the valence band to the conduction band is just astronomical, which is why when we look at our nonmetals, they tend to be non-conductors of electricity. It's not easy for electricity to pass through because we have to have enough electrical energy to clear that band gap. Semi-metals are in the space in between. Those semi-metals have changed their properties enough that band gap has shrunk a little bit, which means we can put electrical current in, causing electrons to jump. Okay? It's larger than we would expect for a metal, but it's significantly smaller than it is for the nonmetals. Does that kind of make sense? The properties that we talked about to contribute to that had to deal with electronegativity. Our nonmetals are very, very electronegative, and our metals are very not electronegative. Okay, so it has to do with how those individual materials are holding on to their electrons. Nonmetals tend to hold on to them tightly, which means they create stronger attractions between fewer atoms, whereas our metals don't hold on to their electrons tightly, which means they have very weak attractions between the individual materials or atoms within our structure, and that tends to create this sea of electrons. The semi-metals float in that gray space in between. So with that context, we could then shift to, ignoring that, okay, ranking the elements from smallest to largest energy band gap. How would we go through and do this? The first step is to separate your metals from your nonmetals. So we can see phosphorus is to the right of our staircase, which means it is a nonmetal. Iron is a metal. And then gallium is on the metal side. So if we're going to evaluate this, the iron is going to have the smallest band gap. And then we would have to deal with our phosphorus and our gallium. Since phosphorus is on the non-metal side, it should have the largest band gap, which leaves gallium in between. So we could go iron, gallium, phosphorus. Okay? So this question is deceptive in that it doesn't need to be this big convoluted thing. We're really just asking you to consider where the elements are located on the periodic table. Make sense? Okay. With that knowledge, we can then go through and look at silicon. Silicon's been used as a semiconductor. Right? And so what we end up doing is trying to mimic that system as much as possible. So if we look at silicon's valence shell, it has 4 valence electrons. Your orbitals are half filled. And so to mimic that system, we can come up with composite materials. This is where we reference 3,5 materials and 2,6 materials. Okay? So 3,5, gallium is a 3 material, arsenic is a 5 material. How do we know that? What is that? What do those numbers reference? Say again? That's the valence electrons. How do we know what our valence electrons are for our individual elements? Okay, we can go through and count the number of columns across. There's another way. No, we don't even want to deal with Lewis structures because the only way you get to Lewis structures is by knowing the valence. Lewis dot structures still, to draw those, you still have to know the valence electrons. So how do you know the valence electrons?
Roman numerals?
Literally the Roman numerals at the top of the column. Okay? Those Roman numerals give you the information about how many valence electrons you have, so you don't have to count the number of columns. It's up to you how you want to do it. Both of those processes work. Okay? So what is an LED light doing to work? Okay, what's happening is you are energizing electrons from your valence band up into the conduction band. So you put in enough voltage to cause that jump. Okay, this is at a very simple level, and we'll look at it in a little bit more complexity a little bit later. Okay, when that electron relaxes back down from the conduction band back to the valence band, okay, so we push an electron up with energy in. When the electron comes back down, we've got a loss of energy. That loss of energy corresponds to visible light. Right? In the case of an LED. Right? So that emission of light is what's producing the LED lights that we've got. Okay? Can you have LEDs emit different light? So could it emit ultraviolet light? Or could it emit infrared? Yeah. All you're doing is changing, you're tuning the size of that band gap. Right? That band gap is directly tied back to energy. So if we're looking at infrared, what kind of energy is that? High or low? And you're like, dang, I don't know how to do that. Go back to the visible spectrum, because the visible spectrum can help us out. Right? In the visible spectrum, what are our colors? Didn't think that was a hard question. That was the Roy G. Biv. Okay? So infrared, is it closer to red or closer to violet? Red. Okay, so we've got that. Does that make it high energy or low energy? Okay? And that can be a hard question. So to answer that, usually what I would go out and do is reference what we deal with in Arizona, particularly during our summers. When we step outside, we try to protect ourselves. We try to protect ourselves from two things, technically. What are those two things? UV, ultraviolet, and then thermal energy, the heat. Okay? The one that we're typically most concerned about is the ultraviolet, because what do? We smear on sunscreen to protect ourselves from that ultraviolet light. Why? What is the ultraviolet light doing? It's causing cancer. Well, how is it causing cancer?
Damaging skin cells.
Say that again?
Damaging cells.
How is it damaging the cells?
By being such a high energy wavelength.
There it is. The ultraviolet light is such a high energy wavelength that when it impacts our skin cells, it's causing chemical reactions to happen. It's the ejection of an electron, right, to different energy orbitals. How that electron relaxes back down can cause cell damage. And if you get cell damage, one of the things that can come along with that is cancer. Okay? Doesn't have to necessarily correlate. Cell damage could just result in cell death. And your skin falls off. That's called a sunburn. Okay? But if you do that enough, sometimes you'll get a cell, or two or three, okay, that doesn't die off. And it now causes a cancer issue. Okay? So the ultraviolet light is a high energy particle. That's the thing that we're concerned about. Well, ultraviolet, is it closer to violet or to red? Is ultraviolet closer to violet or red? It's closer to violet. So which light was higher energy? Violet. We've got a natural tendency to build that in, which means if we're looking at infrared being closer to red, red's as far away from the violet as we can get, infrared is going to be lower energy. And if it's lower energy, what does that mean about the size of the band gap? It's a smaller band gap. Okay? The band gap ties to energy. The thing that you might be thinking of is its wavelength. Wavelength and energy are inversely related. Band gap is directly related to energy. Okay? They're the same thing. But if we're now talking about the wavelength, if I get a smaller band gap, i.e. smaller energy, what does that mean happens to my wavelength? I get a longer wavelength. That's pulling up your 151 content. Okay? Which then sets us up with this. Right? Technically a blue box, but we're going to talk through it kind of fast. Okay? So the size of energy band gap depends on the identity and composition of the elements. So what trends do we notice? Okay? So one of the trends that stands out that most students jump on, okay, which is fine, is looking at the energy doing what? What's the energy doing as we move from 4.23 times 10 to the negative 19 through? It's decreasing. So we're getting lower energy and higher energy. And as we do that, what happens to the wavelength? Small wavelength, large wavelength. Okay, so they're inversely related. Okay, and so I think this particular slide gets a little bit misconstrued because you then start to go through and evaluate all of those columns to the right, those three columns. We could talk about the color of light coming out of it. Okay, but what this slide is actually trying to get you to do is to look at the elements relative to the energies. So really this wavelength transition isn't something that we're actually concerned about. What we're concerned about is what's happening with the individual materials and the energy of that band gap. That's what you need to be looking at, and that's what you should be discussing at your tables. What do we see? Okay, so what we should be doing when we're talking about what we see here is evaluate where we see these elements on the periodic table. So if we look at silicon and carbon, we're looking at row, mind you, not columns, rows. We're looking at 2, come on, pen, 2, 3. When we look at gallium phosphide, what are we looking at? I think that's a 4 and a 3. If we go in that sequence. Helium is your group 1, so gallium's in that 4th row. Okay, phosphorus is in that 3rd. What happens with the gallium arsenide? 4, 4. Okay, so what's changing? We could go through and say 2, 3. Well, that's roughly, and this is a bit of a silly statement, but we're going to do it anyway. That's in row 2.5. Right? Because it's a mix of 2 and 3. What's the 4, 3? 3.5. What's the 4, 4? 4. Okay. What's changing as we move down our column into those rows? So there's a couple things that are changing. The easiest thing that's changing, the band gap is getting smaller. Why is the band gap getting smaller? What else is changing as we go from 2.5 to 3.5 to 4? The size of your individual atoms is getting larger. The larger that atom is, the smaller the band gap becomes. This was one of our conversations when we talked about electron configurations. Okay, if we looked at 2s or 2p's, the 3s and then our 3p's, you'll note the gap between them gets progressively smaller and smaller. Okay, that was 151. The gap between your filled orbitals and your empty orbitals gets smaller. That sounds an awful lot like the valence band and the conduction band. So the bigger your atoms get, the smaller that band gap is going to become. Right? What else could we look at? What else is changing as we go down? Electronegativity. Right? Your most electronegative is in the upper right. Your lowest electronegative is the lower left. Okay? So we're also seeing a trend with electronegativity. And that's probably because electronegativity and size are heavily related to each other. Okay? That connection has not been well formed yet. We're still actively studying that and trying to determine what makes these materials act the way they do. What we currently have are just observations. The more electronegative the element, the higher the band gap. The lower electronegativity of the element, the smaller the band gap. And we can push on size the same way. Right? The smaller the size, the larger the band gap. The bigger the size, the smaller the band gap. So what you need to be able to do is to look at periodic trends and say, how do those periodic trends manifest into the energy of that band gap? And the two things you're looking at is electronegativity and size. Kind of make sense?
Would that be on our quiz, or is that something good to know?
This would be a reason why I'm heavily emphasizing this content. Right? We're talking about how that band gap changes. And if you go back and look at even the practice quiz has questions about how these things navigate. To be able to answer these types of questions, you have to be looking for those trends and transitions. So is this relevant to your quiz? I'm spending time talking about it, aren't I? The next thing that we encounter is doping in semiconductors. Right? Similar to doping in humans, what we're doing is trying to change energies. Right? So there's two types of doping that we can do. Right? We can add a small amount of another element that has more valence electrons, right? Which is going to double back to a question one of your colleagues was looking at within the previous slide. If I can get back to it. If we look at these materials, gallium and phosphorus. Gallium was third, phosphorus was 5. Gallium was third, arsenic was 5. But when we look at silicon and carbon, you're like, well, that's not 3 and 5. What is silicon and carbon? 4 and 4. Okay, with our semiconductors, silicon's our primary semiconductor. That's the thing that everybody's trying to mimic. So why do we have 3, 5? To mimic silicon. Right? So silicon is the thing that we hit when we're talking about semiconductors. 3, 5 mimics the valence electrons of a single silicon atom. Why would we move to 3, 5 as opposed to silicon? Well, what else is changing when we go to gallium and phosphorus? Size of the atoms. And if the size of the atoms change, what else is going to change? The band gap. Why do we want the band gap to change? Well, that band gap relates to the excitement, the amount of energy necessary to cause an electron to be excited, or the amount of energy released when the electron relaxes back down. Right? If we only have one band gap, how many different LEDs do we get? 1. Because that would correspond to a single wavelength. That's all we get, one color from our LEDs. And since we can get varying ones, that means we can tune the band gap. We can control the energy necessary to relax. That can happen by changing the individual material itself. It can also be altered and tweaked by doping. And in doping, what we do is we add another element into the material. That element changes the valence electron states. Okay? And ultimately what it's doing is it's adding small amounts of microstates in between the band gap. So it doesn't change the overall material, but what it does do is provide other steps for how our electrons can move. Effectively, that changes the band gap, okay, for our overall process. There's 2 ways that we can alter that. Okay? Again, it centers back on silicon. Silicon is our 4 valence electron material. So if I'm going to do N-type doping, what I'm doing is adding a small amount of an element that has more electrons than that 4-type. So what elements have more electrons than a 4-type?
What's to the right of it?
Everything to the right of it. Okay? So I'm not saying phosphorus, sulfur, chlorine, and argon. All of those do have more electrons, but I'm also saying arsenic, selenium, and bromine. I'm also saying antimony? Cool. Tellurium and iodine. Bismuth, polonium, and actinium, something like that. Okay? All of those are to the right of it. So using any one of those elements will now be an N-type dopant. because what you're doing is adding an atom to that system that has more electrons than our bulk system. Okay? N for negative. We're not creative. Well, what if we picked an element that had less electrons? Well, if it has less electrons, what we're now adding are holes. There are spaces where we could put an electron because there isn't one yet. Okay? Those are empty spaces, and an empty space is typically known as a positive. So you're looking at p-type dopants. So what could act as a p-type dopant? Anything to the left of what?
The base.
Of our core system, which is 4 valence electrons. Okay? So all elements to the left of that fourth column are now p-type dopants. That's a lot of elements. Any one of them will do. Okay? Why do we pick one versus another? Well, that has to do with what you're trying to do, its capabilities for how it's doping and all of that. That requires active research to decide what's useful and what isn't useful behind that. You don't need to know that for this class. You just need to know that those are possibilities. Okay? So for instance, could I drop uranium in? What would uranium be? P-type. Okay? Probably not a good idea to do that, considering that uranium's radioactive, and that may not be the greatest idea. Okay? But maybe that radioactivity messes with the electron cloud enough that we get some other properties coming out of that. Okay? But that's going to require special reactors to deal with to be able to put these things together. Okay? So, if we're now looking at a silicon-based semiconductor, again, silicon is our base state. That's where everything is going to center. Which of these elements could you use for N-type doping? Which could you use for P-type doping? Again, blue box, figure it out. So, in trying to decide which one would be N or P-type, we could start off at the very beginning and we go GE. Where is GE? GE is directly underneath it, which means it's a 4-type. Does that have more electrons or less electrons than silicon with 4 valence?
Same.
It has the same. So is it N-type or P-type?
Yeah.
It's neither. It doesn't fit either of those categories. Okay? And if that one stumped you, that becomes something that you're going to have to deal with eventually. You can encounter a system that stumps you. What should you do when you get stumped? Move on to the next one. Don't just sit and stew on something you don't know. Move on. Okay? And then you can double back to it later if you need that help. Okay? Or if you have that time. Okay? I can't say N. Just say 0. Okay? What about SB? Where's SB?
5.
SB is our 5-type, which means
N.
that has more electrons, which means it's going to be our N-type. Gallium,
3.
that's our 3-type. That has less electrons, which means
8.
P-type. Indium,
3.
3-type, which means less electrons, P-type. Make sense?
Is there like, if this question were to ask like what is the best ones for p-typing with silicon, would there be a difference between gallium and?
So is there a difference? Yes, absolutely. There's a sneeze sitting in there. There absolutely is a difference. Is that a difference that you have any of the tools to evaluate?
Probably not,
No.
no.
Okay. So if you were going to move into the semiconductor industry or into a chemical engineering or materials degree, that's where you would start to evaluate that. And even then, what I think is going to come up isn't which one is better, it's what are you targeting? What are you defining as better? Because what you're probably trying to do is to tune that band gap. Right? So one of those materials will tune better than the other. How do we know which one? I think at this point it's purely experimental. Right? But that is way outside of my realm.
You probably wouldn't get a question that has 2 of the same ones for p-type.
Or you would just go through and say, well, they're both P-type.
Okay.
Or they're both N-type.
Electronegativity wouldn't have anything to do with it.
Yep. Yep, it's just whether it has more or less electrons. Oh, wall. Okay. So we have diodes, so this is our LEDs. You're attaching a battery to it. From your battery, you get electron flow inwards. Okay? The electrons are going to flow into your valence band. Your N-type, because it had more electrons in it, is going to create small microstates that are now up in the conduction band. This becomes important because your electrons now come in and they can immediately launch into the conduction band. Okay? Well, now your electrons are like, well, where do we go? They're going to flow naturally into a hole. Where's that hole going to be? In our p-type, which is joined next to it. Okay? And the beauty of the p-type is that as soon as our electrons move across in the conduction band, they will very quickly drop in energy to into our valence band. Why is that special? Well, the valence band, because it was a p-type, was missing electrons. There's some extra holes that allow for the electron to drop into more easily and efficiently. Why is that special? Well, as the electrons drop down, that energy has to go somewhere. That energy has to get emitted somehow, some way. Okay? The way these systems are designed is that that energy happens to correlate to visible light. And we now see light emission coming out of that. Once your electron has dropped back down, it can continue the loop around back through our voltaic cell or into our voltaic cell, and we're now completed our loop with our electron having moved all the way around. Okay. More or less. Probably a whole lot more than what I just described. But this is sufficient for what you need.
I was gonna ask a question that's a little bit, that is probably beyond.
Probably going to break me, but go for it.
It's just, would there, like, where would the internal resistances of that, system come into play so that it's not just like a short circuit?
I believe your internal resistance is actually going to be, because I think what's actually happening is you're dropping that into your conduction band.
Mm-hmm.
There are small steps in the N-type, okay, that are technically stepwise through that band gap, so your resistance is actually that gap.
Okay.
Right? And because you have that N-type doping, you're technically looking at 2 steps upwards to get into the conduction band. So I don't think this image does this quite the right service,
Gotcha.
but my understanding is that's what's actually happening, because it's not the whole material that has that. You have pockets of that dopant,
Okay.
and that is your resistance.
Okay.
And of course, I'm sure somebody with a whole lot more smarts about semiconductors will watch this video and be like, you're an idiot. That's fine. Because that's probably true. I am. Kind of makes sense? Okay. So LEDs are more efficient than incandescent light bulbs. Okay. They don't waste energy as heat, which is a little bit misleading because they do actually produce heat. If you've ever looked at an LED bulb, what you'll see is that it's got metal fins on the outside. What are those fins? Oh, dang, Monday knew. You guys don't know what the little fins are? Heat sinks. Those fins open up, maximize surface area, so the heat that's produced by the LED goes into the fins, and because they're now open to surface area and airflow, you can dissipate that heat quicker. Okay? So while they still have a heat issue, the heat issue is nowhere near as high as it is with our incandescents. Semiconductors in solar cells are ultimately doing a similar process. We just kind of invert that system. There are pictures behind it. Okay? As soon as we're producing that energy, we're getting electric flow, which means there has to be a load on the other end. Otherwise, we don't get the electric current to produce. Okay? So this is why if you have solar cells, you want to be using energy during that time, because that's now free energy. Never mind the fact that you paid for all the solar cells, but okay, that's energy that you want to consume. Otherwise, you would then have to try and store that, which is a whole nother expense if you're talking about home usage. Okay? If you're talking about it on large scale is going to be using batteries so that they can actually store the energy, okay, for later usage. Where does silicon come from? You're taking glass, you react it with carbon. That's going to form pure silicon. and you're going to release carbon monoxide from that system. Okay? Lots of energy. We can talk about worldwide energy consumption. Feel like a jerk, but yay. Okay, we can look at the cost of solar cells have decreased dramatically. Okay, this is probably as we're discovering better and better semiconductors to allow for this. So better dopants and better layering and sandwiching of our systems. We can look at the price of electricity declining. That makes sense. If we have more solar cells, why do we have more solar cells? Because it's been getting cheaper to produce them. We can look at world's energy currently coming from, where it's all coming from. You can see, number one, that our energy demands are increasing, which makes sense. Why does that make sense? More people? Yeah, it's probably the biggest contributor to it.
More electronics.
Okay. We could also look at the increase of electronic usage per individual, okay, also now increasing. So there's lots of expectations that this energy consumption is only going to increase. So we've got to come up with other ways to kind of backfill those systems. Renewable energy is powered by chemistry, so you can go through and look at this system or this little diagram, which I think is actually kind of cool, discussing the individual elements as they are relevant or important to the usage of renewable energies. Okay, so you can look at their value on the y-axis, and you can look at the supply risk on the x-axis. So if we were thinking in kind of a political state, we might be saying, how do we ensure that that upper right-hand corner, all those red elements we have access to, or we have supply chains in place, because without those elements, we don't get our energy independence. So people care about climate change. These next two slides, so people of color, particularly women of color, are the most alarmed about global warming. So what these two are trying to kind of point out is that if you had concerns, and this kind of goes back to the class in general as well, if you've got concerns about global warming or climate change or any of those things, you're not alone. Lots of other people agree with you. This isn't just a vacuum. Despite the political environment, it sounds like, well, it's not that big of a deal. No, everybody's very much concerned about this. You're not alone. You should be aware of that effectively support structure, which goes back to the class. I ask lots of questions in class, and how many answers do I get? Yeah, that's about right. Okay? And you might go, well, I don't want to ask a question because I don't want to be wrong. Okay? Well, how many times has someone actually been right versus wrong with the questions I've asked in class when people have responded? Generally speaking, you're still wrong when you're responding. Okay? That's okay. Being wrong gives you a moment to learn and improve. Okay? And so by not asking your question, you're shortchanging yourself, but you're also shortchanging everybody else in the classroom that I almost guarantee also had that question. But since you never brought it up, that question was never addressed, and you now sit in the dark along with everybody else. So the more that you can speak up and actually ask questions, despite what you think about the overall population, the better off your education system will be, and the better off the world will be when you move to larger scale issues. Okay. Which then gets us into what was supposed to happen this week. Okay? So there are questions that you have about homework or the practice quiz, which is where I would say what we'll transition to right now. I'll actually pause this for a moment. So within that first one, where did you want to look? What's that?
Where do I want to start?
Yeah, where do you want to start?
The nitrogen acid
Okay. So you're asking about this nitrogen. Ooh, I just realized something that makes this question a lot more challenging than I think it was intended. What do you need to go through and do? So presumably you're asking about assigning oxidation numbers? Okay. So how do we go through and assign our oxidation number?
So I would see what electrons would belong to the nitrogen.
So what's our formula to solve for our oxidation number?
The valence electrons of the nitrogen minus
Cool.
the nitrogen, the electrons that has
Valence minus, what word did you want to use?
electrons.
So valence electrons minus what? If you don't know, that's okay.
What it owns.
Yeah. Owned is typically what I use. I just wanted to make sure we're using the same language. So how many valence electrons does nitrogen have? 5. Okay. So how many electrons does it own?
What is 6?
Okay. So if we look at our drawing, okay, it's connected out to a carbon, and R group. R group is definitely confusing. Okay, but R group is ultimately going to reference anything other than carbon or hydrogen, carbon or hydrogen primarily, and it could represent other things, but it's typically carbon or hydrogen. If we go through and take a look at this, at the question, it actually says the R represents a carbon group. Okay, so we could actually make an adjustment here and cause that or call that a carbon. If we're now looking at the electrons that it owns, well, how many of those electrons does it own? You look at each of those bonds, compare nitrogen to carbon. Nitrogen's more electronegative, so therefore the nitrogen owns 2 electrons from each of those bonds, which means it owns a whopping 6 electrons. What does that mean its oxidation state comes out to be? -1. So where's your question?
I think the molecule just made a different form.
I'm gonna bet you have a different question. What's the oxidation state of that nitrogen? -3. What did we just say it was? Oh, shit. What did we miss?
So I was gonna ask the hexagon shape. How do you know what it's connected to? You know, you don't know if it's connected to the end next to it or the end below it or next.
Yeah, and I think this was an unintentional part of this quiz. So there's a couple things that are missing from it, and I think there's actually a typo in the calculation, as was discussed in office hours. Amazing. Someone actually talked to me in office hours. Okay, and we think we found a typo within that key. So let's go back to this system. So there's a couple things that you need to be aware of. We have to make sure that we're looking at a proper Lewis structure. So each of the points should be carbon atoms. Okay, and then it says, remember to add your hydrogens, carbon atoms, and lone pairs to the individual structure. Why? Because it's going to be real hard to determine the oxidation state if you don't know where all the bonds are. Okay, so do you understand the rules on how to add hydrogen atoms or carbon atoms or lone pairs to this structure? That's me asking you. Because that is officially Lewis structure. That's 151 at best. Okay? And even then, I would argue it's questionable that you probably didn't go into this level of detail. Okay? So if you took Chem 130 within the last probably 5 years, you should have a little bit more practice because Chem 130 actually looks at these kind of structures. Okay, what we're looking at here are actually organic structures, and being able to process the organic structures means you need to know all of the assumptions that go into play when looking at an organic structure. I will say when it comes to the quiz, you're not expected this level of detail. So to answer this particular question, you would need to look up a more detailed version of these individual structures, or you would need a little bit more context to be able to build it out. So what's that context? Let's take a look at this carbon. We'll call that a red carbon. How many electrons need to be around a carbon? Okay, and this becomes fun. 4, no. 8. Okay, when we talk about Lewis structures, it's octet rule for a reason. I need 8 electrons around it. I understand where you're going with 4. It has 4 valence electrons that it brings to the party. Okay, but it needs 8 around it to satisfy its octet. If we look at that red carbon right now, how many electrons are around it? 2. It only has 1 bond. Okay, which means we've got a severe problem. What happens? We have to add 3 hydrogens to that carbon to ensure that its octet is met. And if you're like, what the hell, I never learned that. I'm sorry, I don't know what to tell you. All I can tell you is that's the way it works. Okay? If we continue through the rest of this structure, okay, because you said something about those hexagons. Let's take a look at that purple dot. What is that purple dot? The dots are all implied as carbon atoms. Okay? Did you learn that? I don't know. Should you have? Maybe. Yeah. Okay? That's a carbon. How many electrons are on that carbon? 6. It needs to have 8, which means
1 hydrogen.
add a hydrogen.
How is there 6 of those 2 lines?
There aren't 2 lines connected to it. There's 3 lines connected to it. Just 2 lines happen to be in the same space, making what we would call a double bond. Okay? So this allows us to fill in our hydrogens and our carbons. We still haven't addressed the nitrogens and the oxygen. Let's go through and take a look at, we'll call it the blue oxygen because it's nice and on the outside. How many electrons are connected to that oxygen? 4. How many does it need? 8. It's still an octet. We need to have 8 electrons. So does that mean we add hydrogens?
No.
Unfortunately not. We don't add hydrogens. What do we add? Lone pair electrons. Okay? That's part of that context. How and why? It's a rule when it comes to simplifications you would make within an organic chemistry structure. And I would bet what happened is this was created as a question real quickly to get it out so that you had practice. And that was an oversight within the individual build of the question. Which takes us to the last place, our nitrogen, and in particular the first place of where we started. How many electrons are currently shown around that green nitrogen? 6. It needs to have 8, which means lone pair. Which means when I go through to do my count, nitrogen had 5 valence electrons. How many electrons does it own? It owns all 8, which means its its oxidation state is a -3. Does that make sense? Before we panic too much and be like, oh my God, I have to learn all these new rules right before the start of the quiz. No. Okay? The quiz will have these things shown when being asked about it. If you're not being asked questions about those individual oxidation states, you won't necessarily see all that extra information. Does that make sense? Okay. And I promise that. So if the quiz pops up and you're like, what the hell? I don't know how to do all those pieces. You can raise your hand and call me over, and probably 2 things. Well, one thing will probably happen. 1, I'll be like, it wasn't relevant to the question. Stop panicking. Breathe and answer the question that's asked. Okay? Or 2, I'll look at it and be like, oh, crap. I didn't get that time that I wanted to sit down and look at it. Let me draw out the whole bloody structure up on the board so you can see that whole thing. Does that make sense? Okay. So, first, Abigail, are you happy with that? I mean, enough? Okay. Yeah?
What does it mean by R represents a carbon 3?
So R just generically means that anything can connect there.
Okay, it's just one
Right.
bond connected to other
Yes,
stuff.
connected to other stuff. What that R group actually is, said in a slightly different language, would be a handle. So the chemistry of this molecule is being shown here. That R group is just the handle with where or how it connects to a larger structure. Other questions about that? No? Okay, I'm going to ask a question. What was the carbon? It was the bottom one, right?
Yeah, the ones that are right in the nitrogen.
Determine that carbon's oxidation state. Blue dot. Sorry, I just got rid of the blue dot. We'll make it a blue C. I want to know the oxidation state for that carbon. How do we determine oxidation state? How many valence electrons does carbon have? 4. Okay. For the record, if you have to move into OChem, you should figure out your freaking valence electrons real flipping fast. Okay, that makes OChem a whole hell of a lot easier if you've got that part nailed down. Okay, minus the electrons it owns. How many electrons does it own? Okay, so we go through and look at each of the bonds. Let's take a look at the bond upwards. That's 2 electrons. How many of those electrons does it own? Man, that's really tiny. Does green stand out a little better? Maybe a little bit. How many electrons does it own of those 2? 1. Why? It's connected to carbon. They have equal electronegativity, so it's owning 1 of those. So we'll start with parentheses. Okay? To the right. Okay? Bonded also to another carbon, which then means it's only owning 1 of those. How about to the left? Okay? There's 4 electrons to the left. And it owns exactly none of them because nitrogen's more electronegative. Which then means when we go through the system, we're going to get 4 minus 2, and we would get 2 is acceptable. Ideally, you would target in at a plus 2. And if you go through and look at the key said plus 3, okay, which I believe was just a typo. Okay, makes sense? So I wanted to make sure you were aware of that in case you're like, oh, now I get it. And then you go back and look at the answer key and you're like, what the hell? I don't get it now. Okay? So I believe that's only a typo within that system. So for this particular question, what you're actually being asked to do is a whole crap ton of calculations. And I would argue that's where the typo came out, is that someone doing the key got very sick and tired of drawing everything out, and so started to shortcut and just go, oh yeah, that's this one. It's a repeat, it's a repeat, it's a repeat. Because the vast majority of the oxidation states, when you look at both of these structures, are not changing. They're immutable. Okay? So to me, a better question would have been not to assign oxidation oxidation numbers to every single atom, but only to the atoms that changed. How would I know which atoms changed? Literally just look at the drawing. Did the drawing change? Okay, so for instance, out here, did that carbon change? No, which means I'm not going to worry about it. How about the carbon below, underneath it? No. How about that entire freaking hexagon? Nope, none of that changed, so I would erase all of that. How about that top nitrogen? How about the bottom nitrogen?
Yes.
Ooh, it did change. So I might be a little bit careful, make sure that bond is still present so I can see that. Okay, how about the bottom oxygen? Nope, going up around counterclockwise. Nitrogen didn't change, the oxygen didn't change, and that top nitrogen changed, right? Okay, so what I would now go through and do, oops, that one didn't change, right? Now I would focus in on those and say, how did those change? Okay. This does become a challenging thing for students to learn. I would argue this is what you should be learning if you move into organic chemistry or biochemistry. You zero in on the parts of the structure that changed. You don't worry about anything else unless you are forced to address something else. If you don't got to worry about organic chemistry or biochem, don't worry about it. Just determine your oxidation states and be happy. Questions? Okay, determining whether it was oxidized or reduced, what are we going to have to go through and do? We're actually going to need the oxidation states for each of these pieces. We did that bottom carbon, we said was a +2. So we should go through and determine that bottom carbon on the other side. What's that one? So 4 minus, I should make sure we got that out there so we can see it. Okay, it's going to split that. So minus, it's going to get 2 from up there. It's going to split that one. So plus another one, and it gets none of those. So I would get +1. The nitrogens did go through and change. Should I go through and calculate their oxidation states? No, why not? Why is it going to stay the same? Sorry. Yeah, nitrogen was the most electronegative. So while it did change its structure, the bonding arrangements changed. ultimately the oxidation state's going to stay the same because it was more electronegative than everything it was connected to. So we don't have to evaluate the nitrogens, which means the only things we're actually going to have to evaluate would be our carbons. Okay, so what happened with the top carbon? Again, I should stop erasing that piece. On the left-hand side, comes in with 4 minus, rhymes with what you're having right now. It's my favorite rhyme. -1, because you all are having fun. Yeah, there we go. I like the enthusiasm. Okay, we're looking at a +3 for that top carbon. If we go through and look at the carbon on the other side, what are we going to get? 4 minus, it doesn't get any of those, and it gets half of those. So we're getting a +2. So if we take a look at that top carbon, what happened to its oxidation number?
It went down.
It went down is perfectly acceptable. Use a different word. It was reduced, which means what happened to the top carbon? It was reduced. What happened to the bottom one? It was also reduced. What happened to flavin? It was reduced. So in this overall equation, we had 2 carbons change their oxidation states. In both cases, they were reduced. And then deciding which atoms, we've now gone through and identified them. It was that red carbon and that green carbon.
Would there be a case where it's like one reduced, one oxidized?
That can be a case, yes.
Like within the same structure?
So within the same structure, I would state theoretically, yes. But I can't think of any examples off the top of my head. So yeah. I just can't think of any examples off the top of my head. So I wouldn't go as far as saying it's uncommon. It could happen, but you're probably also looking at much more complicated structures.
Even answer part A, you have to draw a circle and then like make room for every single part.
I'll show you how you would answer part A. Oh, fill up. Yay! Yeah, doesn't it? Yeah, again, I would argue, I would bet, because I've done the same thing. Oh, I need this example. I want it to be a biological system because I think biochemistry is important and relevant, and I want to bring it up so people are aware of it, particularly for those people that would have to continue to move on. Here's an example from a biological system that does redox. Here's your structure, sign oxidation numbers, and in that statement of assign oxidation numbers, the only part that was triggering was the atoms that changed. And then the quiz got submitted, and then it was, or not the quiz, the practice got submitted, and it was like, okay, time to write a key and go, oh shit. Oh well, you started this bonfire, and then you fill it out the way it is. I would bet. I could be wrong, but I would actually place money that that's what happened. Because yeah, that's a bit absurd. Other questions?
So overall, it's extremely unlikely to have to do that exact thing on the quiz.
Yes. How likely is it that you would have to determine oxidation states on a complex structure? Yes, that is likely. Okay, will it be this complex? No.
So
Right, and
probably
even
sound like
then,
a much smaller version of this then?
yeah, a much smaller of this version makes absolute sense, and I would argue you might even be told to just determine it for the relevant atoms. Again, I don't know for 100% fact, but it's not going to be this complex. And if it is, I'm going to edit. Is it still recording? If it is, I would totally grade it as it. Question?
For analyzing these structures in the oxidation numbers, are we just gonna assume that we're always gonna have to put like the lines around and through the bonds? Or is there specific wording to like look for?
I'm like reading the question, I can't see where it asks like to. Where it asks to like do all.
Yeah.
No, like, I can see exactly what it's.
So, yeah,
there for. I just want to know if I have to replicate that on the quiz.
no, what you would need to replicate is however you're labeling, you would have to make sure you could tell me that particular carbon atom. And so I say that particular carbon atom. Which carbon atom am I talking about? Yeah, it's really hard, right? I just said it's that one. Okay? So I want to say that this carbon atom is a +3. Does that work? Yeah.
Okay.
Okay? Do you need to show the calculation that we went through and showed? Does this show any of the calculation? No. I would argue you should, because you might easily make a typo and screw up the math. So by writing out that math, you can better ensure that you're going to get the answer right. But if you are confident, then you're confident. Does that make sense? Yeah. For this structure, all you need to do is tell me what the oxidation state is for that atom. Because, yeah, the work there is 4 minus 2. I think you can do that in your head, and so forcing you to show work is not appropriate. Next question. And you're like, that means we get to leave early. No, it doesn't. There's tons of friggin' practice. Ta-da, here you go. You don't have questions for me, I got questions for you. Write the balanced overall redox reaction. I almost want to make this more difficult. Never mind. We'll just leave it at that. Write the balanced overall redox reaction, determine what was oxidized, what was reduced, what are the oxidizing and reducing agents. So, the equations given. What happened in each of those equations? Say again? Our chlorophyll was reduced and our oxygen was reduced. So both those equations are reduction equations. Okay, what I was hoping for on the next slide was to also see the E cells. Okay, so the E, sorry, it's not going to be, God, I can't write anything down. So our E reduction potential for this top one, let's just say E reduction, is some number, and this one is some number. Okay? And one of the most common things that I've seen people try and go through and do, let's say this one was negative and this one was positive, 0.2, negative 0.4, I don't know, let's just stick with that. Guys go, oh, okay, well, I want to go through and flip the bottom equation. Why should I flip the bottom equation? That makes a positive E cell, which is a fantastic approach when you're being asked to solve for a voltaic cell. What are you being asked to solve for? Before we even get to oxidized or reduced, we're being asked for the overall reaction. The overall reaction means one of those equations has to get flipped. Which equation needs to get flipped? How do we know? We have to go back and read the initial prompt. Make sure you're paying attention to the prompt within the quiz. This says chlorophyll gains electrons from water. Right? So if chlorophyll is going to gain electrons, dang it, I set them up the wrong way. Make sure that was negative and this one was positive. Okay? If chlorophyll is going to gain electrons, I have to look at my chlorophyll reaction and say, where is it gaining electrons? Is it currently getting written to gain electrons? Yeah, which means I don't flip that one. Okay, where is it gaining electrons from? From the water, which means in my chemical reaction, I need the chlorophyll plus our electrons to our chlorophyll, and I need that water, whoops, that says 2 water, to be a reactant. So I have to flip that bottom equation. So we're going to get our chlorophyll plus our 2 water. We could now add these together and get our overall reaction. One of the problems with this overall reaction is going to be what? The electrons aren't going to cancel out. So what's the lowest common multiple between 4 and 1? 4. So how do I make the 1 into a 4? Multiply by 4. And if I'm multiplying by 4, I have to multiply everything by 4. And so I would get 4 chlorophyll plus my 2 H2O. The 4 electrons will now cancel out on opposite sides, and I would get 4 chlorophyll plus my O2 plus my 4H plus. Make sense? Okay, we'll take that as a yes. So that's now my overall redox reaction. What is oxidized and what is reduced? How do I figure that out? Right. Well, in the first reaction, what's happening? I'm gaining electrons, and therefore it was reduction, which means oxidizing agent. In the second reaction, electrons are a product, which means I have lost electrons, therefore it was oxidized, which means the reducing agent. By tying all of those concepts together, I ultimately answer all of the questions in kind of one fell swoop. Kind of make sense? Questions? Okay. Next layer. Come on, next layer. Calculate the E cell and delta G for the equilibrium constant for the overall reaction. What do you need to go through and do? There's also a typo in this. This should have a 4 in front of it. What do you need to do? Right? We already wrote out those equations. We flipped one of them, right? Okay, which one did we flip? We flipped the bottom one. And if we flip the bottom one, what happens to our cell potential? I also have to multiply it by a negative, which means my overall cell potential is going to be 0.9 minus 0.82, and I get 0.0. Dude, I totally had that and then lost it. Okay. Is this a spontaneous reaction? Yes, a positive cell potential is spontaneous. Okay? And if you're struggling to remember that, that better show up on your cheat sheet so that you've got access to that. And I would argue really big at the top of your cheat sheet because this question shows up a lot. Okay? What do you expect is going to happen to your delta G? The delta G should be negative. What should happen to your K? Don't stress. You've got an extra 2 weeks before the final. You're responsible for knowing the relationship between delta G and K. What should your K be? If it's spontaneous, what is favored? Products or reactants? Products, which means the concentration of products is bigger than your reactants, which means your K is bigger than 1. Those quick checks can at least put you in alignment so that when you go through to navigate all of your calculations, hopefully you get your calculations correct. Does that make sense? How do we calculate the delta G? Negative NF and then our cell potential. Do we have the cell potential? Yes. Do we have N? Yes. Do we have F? Yes. Do we have N? Okay. Is it 1 or is it 4? 4, because we have to realize the electrons had to cancel out. So our number of electrons transferred is the number of electrons in our overall system when they canceled. So our N is going to come in to be 4. for what? Moles of electrons. F is 96,485 coulombs per moles of electrons. What am I asking you to make sure you provide? Units, why? Go back and look at your old quizzes. How many times have you lost a point for not specifying your units? If the question asks for units, you need to make sure those units appear in your calculation. Not at the end of the calculation, in your calculation. Right? And then I already forgot the last one. What's our cell potential units? Volts. We can now punch it into the calculator, and what are we going to get? A number that will be negative. How do we calculate K? There's technically two ways to calculate it. Say again. Cool. 3 ways to calculate it. Concentration of our products over the concentration of our reactants. Do you know the concentration of the products? Do you know the concentration of the reactants? No, okay, so you need another way. How else do you calculate K? Say again? Negative RT ln of K. That doesn't allow me to solve for K. What does that equal? That equals delta G. Do I know delta G? Yes. Do I know R? What is R? Fair. What is the number? 8.314 units. Joules per mole Kelvin. Do we know T? 298. Good. Do we know K? No, but now we can rearrange algebra and figure out what it is. Does that make sense? Okay. One of the things, because I goofed in the last class, when we go through to solve for what K is, K will equal negative delta G over RT. What is the sign on delta G? Negative. When we solve for our K, you got to make sure the negative here and the negative for your delta G appears in your expression. Because if it doesn't, what happens? You get a wildly wrong answer. Okay? So make sure you track those minus signs as you navigate this. Okay? With that, we've reached our time, so we've got to be done. Quiz is on Thursday. If you got questions, feel free to show up